Hey kids, it's Math here. Got DNS solutions for chapter 2. This is going to be a little more bonding, intermolecular forces, really a pertinent topic, I think, in most years, even more so probably this year. So let's take a look. First question here, as most of these questions are, very descriptive, very word-based, very explanatory, and we like those kind of questions. We think that's going to have a lot of reference to us for the AP this year. So as we take a look at question 1, it says, use principles of chemical bonding and or IMFs to explain each of the following: that iodine has a boiling point or melting point of 113. Iodine is a solid at room temperature. The melting point of chlorine is negative 100. It's a gas at room temperature. So why would that be? Well, best thing I could say is these are both nonpolar molecules. Therefore, LDF is the only intermolecular force. Every one of these abbreviations is fine to use on the college board, all right, is the only IMF. Since I2, not is, but I2 has more electrons, it's going to have stronger IMFs, resulting in a higher melting point. So we don't have to state the melting point at the beginning. It's a good thing to bring it back at the end. It wants to know, why is this happening? It's happening on a molecular level, a bonding level. These are both nonpolar. That's my bonding answer, okay? And therefore my IMF answer is they're LDFs only. And since I2 has more electrons, more or stronger IMFs, higher melting point. String together simple concepts to prove what you know. Don't assume they think you know anything. They don't know you. All right? Let's look at B. B is a neat question. It says solid Ag, so Ag solid, and Ag molten, which would be Ag as a liquid. That's what molten means. We've melted it. Okay? Both of these conduct electricity. However, solid silver nitrate is only a good conductor when we melt it or dissolve it. That would take quite a bit of energy to melt AgNO3. It's ionic. It's going to take a lot of juice. So as a solid, it's a poor conductor. How come? Because Ag solid and Ag liquid have mobile electrons. That's also described as a sea of electrons which are free to flow. Flow and conduct. So why do they do it? They do it because. Now, we could come back also and say, why does AgNO3? Well, once we put AgNO3 solid into water, now we have Ag plus and NO3 minus, and these are ions that are free to allow electrons or charge to flow. Not long answers, simple answers, very sequential answers. Okay, so that's our conductivity question. Now let's look at C. We're going back to IMF. C wants to know, we're going to compare H2O to H2S. This is going to be very straightforward. H2S is going to be polar. It's going to have dipole-dipole forces, but we all know that H2O is also polar, but more polar, and it's going to have dipole-dipoles and hydrogen bonds. H2O has stronger IMFs. And that's going to lead to a higher boiling point. Basically the same question as in number 1 in 1A. 1C and 1A are the same. One's melting, one's boiling. Still the same answer about molecular forces, intermolecular forces. Okay? In D, now we got to get down to bonding. They haven't really asked a bonding question. What they want to know is how come Na3AS can happen, but also that we could form AsCl3. And what we say here is NaAs is an ionic bond due to electronegativity, whereas AsCl3 is a covalent bond as dictated by the electronegativity difference. That's really all we need to go into with that one, is how come it can behave as such. And this is arsenic that's acting as a metalloid. It can act as an anion or cation conditionally. So that's our writing question for intermolecular forces. Now let's see what we've got for our Lewis structure question. Very common to have a Lewis structure question. Ours is going to be carbonate today. We did this in class. And I think it's worth visiting again. They use this term trigonal coplanar. Yeah, we're just gonna, don't get that co thing going on. Trigonal planar, right? They gave us that initially. And they're telling us, draw a Lewis structure dot diagram for any of the 3 equivalent contributing resonance structures. Do we have to draw the resonance structures? No, draw them one. So I'm just going to do what they asked me to do. I'm going to draw an oxygen to a carbon to an oxygen to a carbon, lone pair, lone pair, lone pair, lone pair, lone pair, lone pair, lone pair. Remember, it's an ion. No brackets, no charge, no credit. Got to put those brackets on there. Okay, you can put that double bond anywhere. You guys know this already. It resonates. That double bond could be left. That double bond could be right. I put the double bond down at 6 o'clock. Doesn't matter. B says, discuss the hybridization of the atomic orbitals on the central carbon atom that is most likely to account for the bonding geometry and distribution of electrons within this. Include the role of sigma and pi bonds in determining geometry and electron distribution. So what I would say, B, we can sneak this in over here, is carbon has 3 sigma and 1 pi bond. Pi bonds do not affect hybridization. So 3 pi bonds, 3 sigma bonds, my apologies. Whoop. 3, third time's a charm, 3 sigma bonds. I don't even know what I was saying at that point. 3 sigma bonds forms an sp2 hybrid. And if you're sure you know what your answer contains, here's where my money is. It's sp2, 3 sigma, and 1 pi. Underline it. How cool is that? Now as a grader, I know where you're telling me to look. I'm okay with that. All right. Tell me what you think I should be grading. Okay, now question 3 says, draw a reasonable three-dimensional representation of this. I'm going to fail. I can't do this. I can't draw it. You know, you guys understand they're looking for an oxygen, carbon, oxygen, carbon, oxygen, then, and those are my, these are my in the planes, but then they're looking for something here for this double bond, which would be out of the plane. I can't do it. I don't think they'll ask you to do it, so don't worry about that too much. Instead, let's worry about D. D says use a chemical symbol to identify formulas or ions that are going to be found at the lattice points. What they want to know is what's the representative particle here? And in this case, it's ions. So I don't know what kind of shape it's going to make, neither do you, and you don't need to. You need to know there are ions at the lattice points. Hey, looky there. That gives you a great answer for some ions, lattice points, crystalline structure. Kind of cool. They're just looking to see, do you know that the representative particle here is an ion and not an atom or a molecule? Okay, 2 questions down. What's our third question? This is a really cool question, and it uses two of the College Board's darling molecules. These are molecules that they like. Azide, N3, and iodine, I3. Both of these are minus. So A wants us to draw the Lewis structure for each. So we'll draw the azide first. We'll put an N, double, 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 double. Angle the lone pairs, doesn't matter. This is what your azide looks like, but it is an ion. Make sure you draw it as an ion. Now let's draw our iodine. Dink, dink, dink. Single. Come on, Steve. Single to an iodine to a single. And we have seen this on our homework as well. Draw the Lewis structure for each of the ions. Indicate the electron pair geometry. Remember, that's just what's the generic geometry of it. In this case, the electron pair geometry and the linear and the molecular geometry are the same. For this molecule, they're both linear because it would be 2 bonds and the double bonds aren't counting. Remember, these are only counting for geometry, the sigma bonds, not the pi bonds. So it's going to hybridize like 2 and 0. In this case, down below, we've got a central atom iodine that has 5 lone pairs. And so it's linear, it's electron pair geometry. Whoops, I'm sorry. My electron pair is 5 pairs. 5 pairs is trigonal bipe. But what's my molecular? That's the actual molecule shape that it makes. My molecular shape is linear. Okay. They would also like hybridization as it applies. Let's go SP and let's go DSP3 or SP3D, whichever one you choose. That's okay. Don't worry if you don't understand electron pair versus molecular. You stick to molecular geometry, which is the shape of the actual molecule. That's what we're looking for here, okay? And then in C, the last thing you want to know is which, if any of these, has delocalized pi bonds. Well, they're green. They're looking right at us. And the answer there, let's give them a good answer. So we've already done the answer to B right there. And the answer to B was right there. Now the answer to C is azide has delocalized All pi bonds are going to be delocalized because they're not centered around the axis of the atom. They're centered perpendicular to the atom. That's what makes them delocalized bonds. Azide has delocalized pi bond as part of the double bond formed. So there we go. Nice little bonding review. We had hybridization, molecular geometry. We had Darling molecules. We had ions. We had resonance. We had a lot going on in this one little bonding 3-question structure. There's a lot going on in bonding. I think it's going to be a very major topic. It's generally somewhere between 7 and 12%. I think they're going to hold true with that again this year. I'm Smath, and I sure hope this video helped you.